Good morning, everyone, and thank you for joining me. Now I'm speaking to you from rural Spain, where not only am I and my laptop slightly thermally challenged, but also I don't think the internet will be capable of allowing me to make this presentation in person. So I hope that this recording will still be thought-provoking. In case you don't know me, my name is Virginia Toy. I work at Johannes Gutenberg-Universität in Mainz in Germany, and have done so only since last September. Prior to that, I was based in New Zealand, where I had a long history of doing research related to New Zealand's Alpine fault zone. And so I've chosen today, in the context of the workshop and meeting that you're all engaged in, to present to you about the Alpine fault zone in New Zealand. And because the session is entitled The Evolution and Transient Behaviour of Shear Zones and Fault Zones, I plan to talk to you for the next 25 minutes or so about some of the ways that the Alpine fault zone in New Zealand displays transient behaviour, and to talk to you in some ways about what I think some of the evolution of deformation processes has been within this fault zone. Now, before I get underway, I really would like to acknowledge the fact that I've not done my research on my own over the years. And I particularly, in this presentation, owe thanks to Richard Norris, Steve Kidder, Sue Ellis, Dave Pryor, and Hans Vremod. But really, there have been numerous postgraduate students and collaborators who, over the years, have contributed towards advancing my understanding of this major coastal fault zone, and they should all be thanked. Now, I had a look at the group discussions that are planned for after you listen to my keynote and the following one by Whitney, and I noted that there are three major topics, or three major breakout groups. And as I read through the titles of those breakout groups, I thought, it's fascinating that, that I can think of processes of relevance to each of those titles that I think occur within the Alpine fault zone. And so I planned this talk to highlight those. Now, I'm not sure that much of what I have to say is extraordinarily cutting edge and new. I think that to get those results, you need to go to younger researchers or to my PhD students or postdocs. Instead, I wanted to think about these ideas and the concepts that I have thought about within the Alpine fault zone over the last 15 years, and to think about just some ideas that I have proposed over that time as kind of stimuli, as kind of to remind you of those ideas and to provide them as stimulation for you to consider, how do we take these concepts and move forward with them in future research, or how do we say, yeah, those ideas are wrong or can be advanced. Yeah? So the ideas that I'm going to talk about, firstly, and actually I will present these in the reverse order to what's illustrated in this slide, but your first breakout group, which is about deformation across the brittle ductile transition through the seismic cycle. To address that idea, I'll tell you a little story about stress and strain rate variations over seismic cycles and how they're reflected in the grain size record in mylonitic rocks. For the group who are considering processes controlling delocalization, well, many years ago I proposed a wee story related to, or idea about inheritance of crystallographic preferred orientations and the effect that these have on strain localization or subsequent deformation as you move a shear zone rock through pressure and temperature space, but without changing the deformation kinematics or geometry. And I'm going to remind you of that and also put that in context of, well, there's a second part to the story, which is that there are changes in phase distribution with progressive deformation within this fault zone, and the interplay of these two effects actually may control what I think is quite an interesting story of delocalization with progressive deformation in this shear zone. And finally, related to the evolution of shear zones across different spatial and temporal scales, well, I'm going to focus on large scale, which is a big crustal scale fault zone and shear zone. So I don't think I'm going to be addressing that so much, but I do want to say that there are some very recent research ideas that support a new interpretation of the temporal evolution of the Alpine fault zone, really just published last year, and these certainly have implications for how the localization or delocalization processes that I think act might occur. And so, in fact, to start the talk, I want to review this recently published research by Uwe Ring and his co-workers. So that will be the first thing, but firstly, before all of that, the Alpine fault zone in New Zealand, for those unfamiliar with it, is the tectonic plate boundary between the Pacific and the Australian plates as it transects the South Island of New Zealand. And it's a transgressional dextral reverse fault zone. It's accommodated, or presently accommodates, slip at 25 millimeters per year dextral, and reverse slip that accomplishes uplift of the hanging wall at up to 10 millimeters per year. Coupled with high rainfall, this results in extremely rapid erosion, and consequently the shear zone uplifts materials from a depth of up to 35 kilometers very rapidly, or at least we always thought very rapidly. The rocks that are incoming to the fault zone were originally trench-fill sediments, so they're quartzo-feldspathic, originally sandstones, mudstones, and a little bit of metabasite. And they were progressively metamorphosed during, in fact, 2 phases of metamorphism before they were buried in the modern, or the second phase of metamorphism was burial in the crustal root of the Southern Alps. And they were raised there to upper amphibolite or middle amphibolite fissures conditions before being exhumed. And so currently we have the ability in surface outcrops to access a spectacular sequence of fault rocks that are representative of the rocks that are potentially currently forming in the shear zone at depths beneath this modern and active origin. Now, I've done field research in this fault zone ever since my PhD. There have been many, many others who've done similar. We've also, in the last decade, carried out 2 phases of drilling into the fault zone. The consequence of this is that we've characterized the fault rock sequence extremely well. Okay, so a study that does excite me that was recently published, as I mentioned, by Uwe Ring, are new rubidium, strontium, and I think there are also argon ages from muscovites. And these are within, so the fault rocks that are most deeply exhumed have myelinitic fabrics. And they're a reflection of the high strain, high temperature shearing in the base of the myelinite zone. And actually they present a very nice cross section here. So that's the same, it's basically the slice through this block model that I showed in the preceding slide. This is the same image here. You'll see the Alpine fault zone dipping moderately towards the southwest, and you can see that there is a supposedly, and this is fairly reasonable based on seismic reflection surveys, a décollement along which rocks of the Pacific Plate are transported before they're entrained and exhumed along the ramp of the Alpine fault zone to the surface. Now, we for many years have highlighted the fact that the Alpine fault zone itself has probably only been operating with its current kinematics for around the last 5 million years or so. And that's based on our understanding of the plate motion record, which indicates that convergence started about this, or so the fault zone had a dextral component to it for 25 million years at least. Initially, 25 million years ago, it was dextral transpressional, and with time we've seen a change in the relative plate motions across this boundary that has resulted in a progressive increase in the convergence component. And we really think that the fault zone itself, or I always thought for most of my career, that the fault zone became a focused and localized structure that started to exhume the rocks from the base of the shear zone only within the last 5 million years. Now, these new rubidium-strontium ages indicate that amphibolite facies myelinitization within this fault zone primarily was accomplished by 10 million years, and very little has been occurring at high temperature amphibolite facies conditions, so temperatures in excess of 565 degrees C and a gigapascal. There's been very little myelinitization, overprinting myelinitic fabrics that have affected these rocks since that time. So the study, the interpretation that Uwe and his co-authors have come to is that the majority of the myelinitic fabrics we see exhumed within the Alpine fault zone rocks were not in fact developed during progressive shear up this hanging wall ramp, but they were developed during shear along a basal décollement at depth. And this was accomplished pre-10 MA, and subsequently, between 10 million years and 2 million years, these myelinitic rocks, for the most part, were almost statically exhumed along a very thin, I guess, focused shear zone. This is unclear to me and unclear from their models, but there is a thin focused shear zone that has allowed most of these myelinitic rocks to be exhumed without developing substantial overprinting textures until around 2 million years ago, and this is where the argon ages come in. And this was also occurred with very slow cooling, and at 2 million years, these rocks passed through the brittle ductile transition and then experienced very rapid exhumation and cooling at 100 degrees C per million years. And I would adhere that this is probably, the cooling is motivated by circulation of fluids into the fractured hanging wall of the fault zone. Yeah, so this is a slightly different history to what has been conceptually in my mind, and probably, and I would say in a lot of other people's minds, about this fault zone for the last little while, but I actually think that the evidence that they present is very sound and that the model is fairly reasonable. Okay, let's see if we can make this firmly challenged computer continue. Okay, the second part of what I wanted to talk about is the story of paleopiezometry and how it records stress in the Alpine fault zone. So for many years, I have pointed out to people, and it's been recognized by others before me, that most Alpine fault zone myelinites have fairly coarse recrystallized grain sizes. Of order of 100 microns is not atypical, maybe 50. It depends where you look. These are photographs of quartz myelinites taken with increasing proximity to the center of the exhumed myelinite zone, which we think is the highest strain material. And you will notice, looking at them, that most of the new grains, not the remnant grains as you see in this furthest right photomicrograph, but the new grains are of a fairly comparable size and not extraordinarily small. Now, if we apply standard paleopiezometric relationships, these indicate the differential stress that these rocks experienced during deformation was less than 30 megapascals. That's interesting to consider in the context of the model that I just presented to you, which is that the majority of myelinitic deformation was accomplished in a basal décollement, and there was passive exhumation with decreasing pressure and temperature. So maybe, the majority of deformation in this fault zone was actually at high pressure temperature conditions and low differential stresses. That could be true. But it always puzzled us because we thought that these rocks were progressively deforming as they were exhumed towards the surface. And we expected that they should pass through some sort of crustal strength peak around the brittle ductile transition and develop smaller recrystallized grain sizes. When I look at these rocks in high resolution images, we do see that there are a small proportion of finer grains, less than 10 microns. And these would be representative of peak stresses of 100 megapascals or more, as you might expect around the brittle ductile transition. This work was this kind of rigorous examination of the grain sizes within the mylanitic rocks. It was done in some detail by Steve Kidder when he was a postdoc at Otago. This really cool diagram here, he took something like 200 thin sections distributed along the length of the Alpine fault zone, or taken from outcrops along its length. And he carefully measured, using a linear intercept method, the recrystallized grain sizes. And he actually looked at the proportion of various recrystallized grain sizes in each thin section. So here the size of the dots is proportional to the proportion of that thin section that has that recrystallized grain size. And you can see that most thin sections do have this coarse-grained fraction, but they have a small proportion of fine grains as well. The key message from this, for me, is that only a few grains in each thin section preserve the peak stress that these rocks might have experienced during their deformation history. And the story that I've previously put forward to explain this, which I think that this group could consider in the context of the new model of evolution of the shear zone, and also in the context of other shear zones on the planet, is related to this. So many years ago, Dave Pryor did a study where he looked at a quartz band that was deformed around a rigid garnet grain, and he considered the variation in strain rate between the material where the quartz band was wider and where it was impacted by the adjacent rigid grain, and assumed that overall the bulk zone had to accommodate the same bulk strain, so therefore you had a higher strain rate in this region. And he used that study to, and the proportion of material that was recrystallized within each part of this quartz band, to estimate the amount of time that it might take for a new quartz grain to grow during progressive recrystallization. And his estimate was that at a strain rate of 10 to the minus 11 per second, which seems reasonable for the Alpine fault zone and many other crustal shear zones, it would take 5,000 years for a 20 micron subgrain to form, or in other words, 2,500 years for a 10 micron grain. Remember, that's the smallest grain size that we have within these rocks. We need 2,500 years to develop those grains at standard recrystallization rates. Now, another important study that was done some years ago by Sue Ellis of GNS Science looked at these numerical models where she considered the fact that the Alpine fault zone comprises a brittle portion in the near surface and a ductile shear zone beneath. And these are kinematically linked. So episodic failure in the brittle shear zone transfers downwards into the ductile shear zone beneath. And at the base of this brittle fault, accelerated strain rates are associated with accelerated with high differential stresses, but these are only episodically and transiently experienced. And her models indicated that you would have, let me say, you would see a peak stress, maybe 100 megapascals at the base of the brittle zone. And over the interseismic period, you would get a linear decrease of that stress until the next earthquake occurred. Now, we think the Alpine fault zone, on average, has earthquakes around every 300 years. And so if we take Sue's models at face value, we can estimate that we might only have 150 years for which these mylanites at the base of the brittle shear zone are actually experiencing stresses of order of 90 megapascals or more. So if you need 2,500 years to grow a 10 micron subgrain, then you need 15 earthquake cycles in order to develop each 10 micron grain which reflects those peak stresses. And that would assume that each of those small grains is growing again in each cycle, rather than a new site being the thing that is accomplishing or accommodating growth. So I use this idea to point out that it makes sense that we have a very incomplete record of small recrystallized grain sizes potentially showing the peak stresses that these rocks have experienced. Now, I like that story, but again, I want to highlight that if we consider it in the context of the new thermobarometric data that Uwe Ring has presented, potentially these rocks never experienced substantial strain along their exhumation path, and the majority of their deformation was only accomplished in the basal décollement. So maybe there is no requirement for them to be passing through a crustal strength peak. Definitely an idea that's worth considering further. Okay, so the final part of the story that I want to remind you of in my presentation today. So here is a fairly holistic diagram that I actually produced at the time of my PhD. And a version of this was published some years ago by myself and Richard Norris, because it can be more broadly applied if you remove some particular aspects of it to transpressional and reverse lithospheric fault shear zones in general. The thing that I want to highlight here is that this is the basal décollement, this is the Alpine fault shear zone, and these rocks are supposedly progressively deforming through decreasing pressure and temperature as they're exhumed to the brittle ductile transition and then to the surface. And we can consider the fact that each rock that's within this zone experiences no real change in its deformation kinematics, which means that the direction that stresses, or the direction that it's trying to deform in with respect to any existing fabrics does not change over time. However, the rock is experiencing a gradual and progressive reduction in pressure and temperature as it's exhumed towards the surface. And that has interesting implications for the way that strain focuses or doesn't focus with progressive deformation. So a story that I came up with way back in PhD times was related to the evolution of CPO fabrics within the quartz myelinites. I had observed that that pure quartz bands, even within the exhumed rocks, preserved a quite strong Y maximum quartz CPOs, which we would typically attribute to high strain at amphibolite facies conditions, maybe even high strain at Greenwich facies conditions. Conversely, the lower strain rocks, the pure quartz bands within those, had developed only cross girdles or single girdle fabrics, which would be more typical of deformation at Greenwich facies conditions, or at least to lower strains. And the story that I put forward at that point, and this concept was applied by Giorgio Pinocchioni to some deformed veins in the Alps subsequently. The story that I put forward at that point was that these highly strained rocks, when they experienced substantial strain at high pressures and temperatures, where deformation and glide on the Prism A slip system was favoured, they developed the strong CPO that was inherited. And as the rocks were brought to lower temperature conditions and or to lower strain rates, the favoured glide system, which would then be the basal A system, was suboptimally oriented with respect to the deformation kinematics to accommodate deformation. And the idea was that that resulted in basically a form of strain hardening. So the ultramyelinitic rocks, with their strong Y maximum quartz CPOs, were not easily able to deform it as the rocks were exhumed. And an idea that I had at the time but didn't make too much noise about was that this actually might result in delocalization, deformation, or broadening or flaring of the shear zone towards the surface. But I do want to raise that point again because I still think that it's potentially the case. There is one way that I can put forward within this shear zone that progressive deformation results in strain hardening and broadening of the shear zone, and there may be other processes that you can think of that might accomplish similar things. Another aspect of evolution of fabrics within these rocks is that we see that At the surface, the exhumed ultramyelitic rocks, all of these rocks are a combination of quartz, feldspar, biotite and muscovite. That's the dominant phases. As these are, as we look at them in the exhumed fault rock sequence, we see that the protomyelinites, these rocks have accomplished only simple shear strains of the order of 12 or so. They have a fabric that is quite distinct. It still has strongly layered fabric comprising layers of quartz and feldspar and intervening cleavage domains of biotite and muscovite. If we look at the exhumed ultramyelitic rocks, that layering is not preserved well. So in fact, there we see a well-mixed fabric with grains of quartz and feldspar distributed amongst biotite and muscovite. So on the right is a photomicrograph of a typical quartz layer within the lower strain rocks, and remember that this would be bounded by muscovite and biotite layers that are through-going. And then we have a typical photomicrograph of a high-strain ultramelanite with a well-mixed fabric. And I have in the past argued that that these fabrics at top right that are preserved in the quartz layers in the low-strain rocks are a characteristic of deformation by grain size insensitive creep. Whereas these well-mixed fabrics, which also I would say have a weaker crystallographic preferred orientations, are probably reflect a rock that was most easily deforming by a grain size sensitive creep that was fluid assisted and also required grain boundary sliding. Now, those Y maximum CPOs that I mentioned previously are preserved in these quartz bands in the low strain myelinites, but not as well as they are in the rare quartz bands that are still retained within the high strain ultramyelinites. This is definitely, I think this is a reasonable evolution in dominant deformation mechanism with progressive exhumation in these rocks. And I expect that it happens in a vast array of crustal shear zone rocks as they're exhumed towards the surface. A lot of high strain rocks have weakly developed fabrics. Now, I was putting this together, I actually, because I was taking one diagram from out of my PhD thesis, I came across this one that I'd also provided. And in this diagram, I was considering the idea of a pure dislocation creep flow law and what I called a polyphase flow law, which was a combination of dislocation creep of quartz using a mixing law combined with a grain boundary sliding or a sort of frictional viscous flow within the rocks that contain a substantial proportion of muscovite and biotite. And these strain rate curves, which are these strength curves, sorry, I'm not sure how much of that will have dropped out. I'll find out when I replay if I get the opportunity. So let's go back to these diagrams. So these differential stress depth plots show for two reasonable strain rates within the Alpine fault zone. We have two different flow laws plotted. The red dashed lines are dislocation creep of quartz, which at high temperature has low differential stress and is supporting low differential stress and is favoured. And then we also have with the black lines a composite flow law with a sort of frictional viscous flow. And you can see that at the lower temperatures or nearer the surface, this flow law is actually going to support lower differential stresses and be favoured. And I think that this demonstrates in part that it's reasonable to assume that you will see a transition from dislocation creep to a polyphase or a frictional viscous kind of a flow. And I also, at the time, noted that these rocks, at least the proto-Marlinitic rocks, which retain their layered fabrics, if you look at them, they're actually, their fabric looks something like this. So they're actually composed of this layered inherited fabric, and they're also transected by these small localized shear zones that we call shear bands. And I hypothesized at that time that the ongoing deformation at the shallower part of the crust within these shear zone rocks, that we saw a transition from sort of a homogeneous flow in the, or not a transition, but maybe coevally, we had a homogeneous frictional viscous flow occurring in the polyphase, well-mixed ultramyelinitic rocks. And out in the margins of the shear zone, we would see the deformation being focused into these shear bands. And so the same deformation mechanism, the frictional viscous flow, which is favored at the shallowest ductile shear zone conditions, is really only affecting small parts of this rock. So I guess that gives you another perspective on the idea of localization or delocalization. I guess if you take a horizontal contour through the Alpine fault zone, somewhere on the exhumation trajectory, then I would say that you have a broad 100-meter or so thick high strain ultramyelinite zone at the center of the shear zone, and on the flanks of the shear zone, where maybe the whole shear zone is broadening because of the inherited CPO problem, you also see that a lower total strain is accomplished potentially at the same strain rates within a series of very thin cross-cutting and discontinuous on a centimeter scale or a 10 centimeter scale small shear zones. So it would be interesting to plot that as a full strain rate plot with horizontal distance across the fault zone, and to consider how that looks with different depths. I haven't made that plot for this presentation, but it might be something for others to consider. Okay, so just to finish up, I'll bring you back to this holistic diagram of the Alpine fault zone. And I might just leave it there for a minute. Now I know that I wandered over a few different ideas there, and maybe it was clear that I don't feel that I have a full understanding of the way that strain is distributed within the Alpine fault zone at the present time. And every time that a new bit of research comes to the fore, my ideas change again. But I do hope that this group are in a position to consider the various ideas that I've bandied around, and to think about where on the rest of the planet they might be applicable, and what we are going to do to fully define the geometry of strain at different depths within real crustal shear zones in a realistic way in future studies. Thank you.